Hi, everyone. All right, well, we've been able to discretize Laplace's equation, and now I'm going to show you how we can use what we've learned to solve for the potential numerically. Okay, so here's what we found. We found that solving for a solution of Laplace's equation that's discretized onto a grid, that the value of the potential at any grid point must be equal to the average of the value of the potential at the adjacent grid points, as shown here, okay? And now I'd like to show you how we can use this to create a technique called relaxation method, which will let us find the potential. So here's what we should do. First, we need to set up a matrix or maybe a grid of cells in a spreadsheet program to represent the potential. Then we'll set the potential at the edges to fixed values that represent our boundary conditions. These are our boundary conditions. And I said the potential at the edges, but these boundaries could be either external boundaries that go around our whole charge-free region, or they could be internal boundaries, as you'll see in a moment. Then, the interior cells, that is the cells that aren't on a boundary, can initially be set to any value. In our case, we'll just use 0 for the initial value typically, but in more sophisticated versions of this, you can set things up so that you'll get to a solution sooner. And then the next step is the key step. Let me give this formula up here a name. I'll call it formula A, okay? This is the formula that says that the value of the potential at any point is equal to the average of the value at the adjacent points. So what we're going to do is repeatedly apply equation A. That is, we're going to apply this over and over again. And in each iteration, we will set the potential at each point to the average of its adjacent neighbors. Okay? And what we'll find is that after many iterations, the potential will converge. That is, it will reach a steady state in which every point will be the average of its 4 nearest neighbors. and the values won't change with additional iterations. Okay, and that will give us the answer. And then since the answer will satisfy Laplace's equation, of course, approximately, because we're solving it on a grid, and it solves the boundary conditions, then the potential that the program will converge to will be the unique correct potential, at least to within a good approximation. All right. Well, the next thing we'll do is to see how you can actually do this in a straightforward way. And give me a second here.